In regards to the topic of normal probability distribution, we are going to look at normal as approximation to binomial distribution. So we covered standard normal distribution, and in short, it is bell-shaped. The parameters for any normal distribution happen to be mu and mean. Mu equals 0. Mu is 0, standard normal distribution, and sigma is 1. And when we do the applications, normally we are dealing with a normal distribution other than standard normal, and a transformation of z equals x minus mu over sigma can do the job for us. We discussed estimators. In general, the idea behind the estimators is very simple. We are looking at what is known as point estimate for population parameters. So normally we don't have access to population parameters. So therefore we start from somewhere. We start from a sample statistics. So for proportion P, we use P hat. For mean mu, we use X bar. And for variance sigma squared, we use S squared. Needless to say, some estimators are better than the other because they are unbiased, and some are not. When we say unbiased estimator and it targets the population parameter, we mean the sampling distribution has a mean that is equal to the corresponding population parameter. Therefore, as an example, we could write mu of P hat equals P. CLT, or central limit theorem, is really the simple case. When this thing works, then we have a sampling distribution of X bar where mu of X bar is equal to mu. But sigma of X bar is not equal to sigma. It's sigma over square root of n. And as the formula indicates, when n gets larger, the standard error of the mean, sigma of X bar, gets smaller. We also looked at methods of assessing normality. We know how to use a TI calculator to graph it. It was explained, and we have it right here. But in short, when you're given a bunch of data, all you have to do, corresponding to each piece, find its z-score and plot the pair x comma y equals to the z-score. Let's go to the new stuff. You're looking at normal as approximation to binomial distribution. So we use a normal distribution as an approximation to binomial distribution. ND for normal, BD for binomial. And when you're dealing with the binomial distribution, you know that you have to come up with N and P, and Q can be calculated. When can we use normal as an approximation to binomial distribution? When NP and NQ, their product is large. How large is good? We need them to be larger than or equal to 5. Now, bear in mind, in some text, they like it to be even more, and they use NP and NQ larger than or equal to 10. So depending on the text, they may have different restrictions, but generally speaking, when NP and NQ are fairly large, then the approximation works out. In which case, mu is calculated as always for binomial distribution. Mu is NP, and sigma is square root of NPQ.
The binomial probability distribution is discrete with whole numbers for the random variable x, but the normal approximation is continuous. To compensate, we use a continuity correction with a whole number x represented by the interval from x minus 0.5 to x plus 0.5.
Recall a binomial probability distribution has a fixed number of trials that are independent, trials that are each classified into two categories commonly referred as success and failure, and trials that the probability of success remains constant.
We will discuss this further, of course, but the idea and the synopsis is very simple. We use normal instead of binomial. Number one, why do we do that? Because generally speaking, binomial is very difficult to calculate. Now, at the very least, it was difficult to calculate. Now with technology is a different story. I want you to know that. That's number one reason. Now, when can we do that? We can do it if the approximation is decent. Approximation is decent in the case where NP and NQ are large. How large is large? Well, 5 is good, 10 is better. That's the bottom line. So what happens when you want to approximate this? Well, remember, binomial distribution is discrete, normal distribution is continuous. So as we move from one to the next, we have to use what's called a continuity correction factor. And why we are adding and subtracting 0.5. This is what statisticians have come up with in order to cover the endpoints. Does it have to be 0.5? No. It even could be 0.4 or even 0.1. But we're going to stick with what they have come up with, those who know a lot more stats than we. And of course, as far as the binomial distribution, everybody remembers that how the binomial distribution works. We have n number of trials, and they are independent. The probability stays constant from one stage to the next. And then we really have, this is the most important part in my opinion, because it's very easy to establish the rest of it, I think. What matters is that recognize there are two categories, and therefore it's a binomial distribution. Now, I think everybody is familiar with the notation. We have seen it when we dealt with binomial distribution. N is the number of the trials, or the fixed number of trials. X is the specific number of successes in n trials. And again, remember success. P is the probability of success in one of the n trials. Now, success doesn't necessarily mean something positive. And of course, Q is the complementary event, 1 minus P.
Rationale for using a normal approximation. Recall, the sampling distribution of a sample proportion tends to approximate a normal distribution. Check the following probability histogram for the binomial distribution. N equals 580 and P equals 0.25. In one of Mendel's famous hybridization experiments, he expected 25% of his 580 P's to be yellow, but he got 152 yellow P's for a rate of, 26.2%. The bell shape of this graph suggests that we can use a normal distribution to approximate the binomial distribution.
This is the graph when we were discussing this concept. Because it's normally distributed, then it makes sense, the concept of an approximation. And again, I can't really emphasize this enough that. So we are going to sound like a broken record, but it is worth repeating this.
Requirements. The sample is a simple random sample of size n from a population in which the proportion of successes is p, or the sample is the result of conducting n independent trials of a binomial experiment in which the probability of success is p. 2. NP is greater than or equal to 5 and NQ is greater than or equal to 5. Approximation is better if NP is greater than or equal to 10 and NQ is greater than or equal to 10.
Some statisticians go with the higher number.
Normal approximation. If the above requirements are satisfied, then the probability distribution of the random variable x can be approximated by a normal distribution with these parameters. Mu equals NP and sigma equals square root of NPQ. Continuity correction. When using the normal approximation, adjust the discrete whole number x by using continuity correction so that any individual value x is represented in the normal distribution by the interval from x to 0.5 to, or x minus 0.5 to x plus 0.5.
And the procedure.
Check the requirements that NP is greater than or equal to 5 and NQ is greater than or equal to 5. Find mu equals NP and sigma equals the square root of NPQ. Identify the discrete whole number x that is relevant to the binomial probability problem being considered and represent that value by the region bounded by x minus 0.5 and x plus 0.5. Graph the normal distribution and shade the desired area bounded by x minus 0.5 or x plus 0.5 as appropriate.
Here's what I'd like you to see for the next page. I don't want you to memorize this at all because I want to explain how it works. The only thing that you need to remember when we go from binomial to normal, we need a 0.5 continually correction factor. So when x is a, we go by 0.5 to the left and right of it. That one we need to know. The rest of them, you really don't want to memorize. I'm going to explain how you arrive at the answer without having to memorize that. Just remember the 0.5 continuity correction factor, just to give you an idea of why it happens right here. Probability of x equals a number, such as 5 or 10 or 15, when it comes to continuous random variable, when it comes to normal distribution, is equal to 0. So if we were to use this one unchanged, when we go to normal, the answer is 0. Why? Because a single value doesn't cover any area. Since it doesn't cover any area, the answer is 0. So to get around that, they have introduced this continually correction factor, and they have agreed upon the number 0.5. And we should bear that in mind. So what happens in this case, if it's larger than or equal to 10, I don't want you to worry about this and remembering this. I want you to see a change happens. Now, how do we change it? I'm going to explain that after I go through each and every one of them. If x is larger than a, then we add 0.5. If it's less than or equal to a, we add 0.5. If it's less than a, we subtract 0.5. And needless to say, mu is NP sigma equals square root of NPQ. Do I have to remember this? No. I will explain it to you so you understand when you add, when you subtract. Okay? So here's a very simple example. Let's make up a number. We are looking at binomial distribution. In fact, let's just write it underneath. If the BD, so I'm going to write probability, let's just write it in front. Okay, probability of x larger than or equal to, let's say, 10. Now, either you have to go with x larger than 10.5 or larger than 9.5. Make sure everybody understands why. And we figure out which one and why in a moment. So what am I saying? You just remember the continually correction factor of 0.5. Therefore, all you know is that you either have to add or subtract. Which one and why? It's very simple. For you to answer that question, and in fact, let me also write probability of x larger than 10 only, and we'll see which one and why. This is a binomial distribution. So what does it mean, binomial distribution? That means probability of x equals 10, 11, 12, all the way to n. Now think about this. What happens if you choose 10.5? What is the first discrete number larger than 10.5? That means what is the integer, okay, or a whole number or a natural number? 11. So what happens? If you write this as a binomial distribution, it's the probability of x equals 10, probability of x equals 11, probability of x equals n. So what happens to probability of x equals 10? If you go this route, the first one is 11, you are going to miss the 10, so that doesn't work out. And therefore, that one is out. You look at the endpoint, make a decision. Now let's look at the next one. What is the meaning of probability of x larger than 10? This is a binomial distribution. This means probability of x equals 11, x equals 12, and it continues indefinitely, which means the first discrete number is 11. So if I said probability of x equals 9.5 here, will not work. Why not? Because the very first discrete number is 10, but we need 11. And because of that, you change it to a normal distribution. X is larger than 10.5. Here you don't have to memorize this. Understand, you look at the endpoint whether it's going to be included or not. That's all there is to it. It becomes more clear as we look at a couple of examples.
Assume that 6% of American drivers text while driving. If 300 drivers are selected at random, find the probability that exactly 25 say they text while driving. Use normal approximation.
We need to figure out what is given to us. So assume that 6% text. So that means if you're looking at texting, you either text or you don't. So there are two outcomes. And of course, everything else follows when it comes to two outcomes. When you have the two outcomes, then they have n trial, they are independent, the probability stays the same, all of the above. The fact that there are two outcomes, it tells us it's a binomial distribution. The moment we claim it's a binomial distribution, we need to come up with the n and p, because if we are claiming that's the case, we need to come up with that. So we are dealing with a binomial distribution. That's the first thing. Now they're asking us to do normal approximation. To do that, we're going to check the work. So we have to calculate the NP and NQ. Needless to say, Q is 1 minus P, and that's how we arrive at 0.94. By now, so because the product of NP is 18, the product of NQ is 282, both are larger than or equal to 5, we can use normal approximation. By the way, as far as quick check, as you can see, Q is much larger than P. So if NP is larger, you don't even have to check the NQ. Okay, so depending upon which one is larger. Whatever is smaller between the P and Q, check that one, and then you don't even have to check the larger one. I mean, numerically, you can guess that it is obviously large. So with that being the case, we want to calculate the probability of x equals 25 binomial distribution. And what we do, let's quickly calculate a couple of things. We need, as always, mu and sigma. So we are going to do a quick calculation of the two. Mu is NP. We've already done that. Sigma is the square root of NPQ. And we do that, we multiply and we take a root. And notice what I'm going to write. I'm going to write binomial distribution. It's important to really understand these steps. So number one, you're dealing with binomial distribution. Anytime you have an equality and nothing else, you just go by 0.5 to the sides. So you go 0.5 to the left, 0.5 to the right of number 25, and it gives you the second step, normal distribution. So what are we doing? Step one, binomial distribution. Step two, normal distribution. Step three, standard normal distribution. So we go from binomial distribution to normal distribution, and now we're going to go to the z. To go to the z, we have to calculate the z. That's why we have already calculated the value of mu as well as sigma. So z is x minus mu over sigma. So we use the top formula to get to the z for 24.5 as well as 25.5. So the z-score is calculated as follows. Z is x minus mu over sigma. So 24.5 minus 18 over 4.11 equals 1.58. Normally, I like to use more decimals. Remember, when you go to your z table, they have a limitation. They go with 2 decimals. For 25.5, the same way, z is calculated. X minus mu over sigma, resulting in 1.82. So now, this is the third step. So I have the binomial distribution, I have the normal distribution, the standard normal distribution. Now, I like to go to the graph. We are looking at the area between 1.58 and 1.8. Take a look. So it doesn't even have to be to scale, but it gives you an idea. So this is the area we want to cover from roughly 1.58 to 1.82, and that requires something, either the Z table or the technology, and it results in, if you use table, results in the difference between the two. Remember, when you go to the positive Z score, you look it up all the way to 1.82, and then you look it up all the way to 1.58. Their difference is the answer. So 0.0227. So find the probability that exactly 25 say they text while driving is about 2.27%. Now, we went over the normal CDF and how we arrive at the answer. To put the normal CDF, you put the lower limit of 1.58, upper limit of 182, mu and sigma, and as you can see, that is the value from the technology versus the Z table. If we were to use binomial distribution, because it's 1 point, we use binomial PDF. If it were between 2 points, okay, remember, I'm looking at, for this case, you use this one. So we use PDF because there's only one value. And as you can see, they are close, 0.0226, okay, 309195 is very close, okay? So that's a decent approximation. That's why it's called an approximation, it's not exact. All right, I'm assuming we are okay with this. We are going to move on, class.
Suppose 10% of the members of a handball league are left-handed. If 200 handball league members are selected at random, find the probability that A, 10 or more will be left-handed, B, at most 15 will be left-handed.
We looked at the case where X had a specific value. Now we are looking at a case where X is less than, greater than, and so forth. So first, let's discuss the given. As we look at this question, we notice that members of a handball league are left-handed. That means what? You're either left-handed or not right-handed. There are two outcomes, two categories. And really, that's the most important thing. The rest really should work. So this is a binomial distribution as a result. Two outcomes, two categories. And so with that being the case, what is N?
200.
Very good, 200. As we read the question, what is P?
0.1.
Perfect. And that's it. You really want to get to the habit of starting with the given rather than just doing the work, because you want to make sure that you read the question and reread the question to understand what is given. So we want to find, by the way, we are looking at the normal approximation specifically for this case. And so can we use this? We have to check the NP and NQ. We have to look at the product of N and P, N and Q, to see whether we can use it or not. So first and foremost, this is given. We are dealing with the binomial distribution. N is 200, P is 0.1. NP is 20, and NQ is definitely larger because Q is larger. And again, Q is 1 minus P, or 1 minus 0.1, or 0.9. Mu is NP. We calculate that. We already have it as 20. And sigma is square root of NPQ. We multiply them. We take a root, and that would be sigma equals 4.24. The next thing is to calculate part A. And to calculate part A, we are asked, we want to find the probability that 10 or more will be left-handed. Okay, what does it mean? It's important to be able to get this out. Binomial distribution tells us probability of X larger than or equal to 10. So this is what I want you to pay attention to. Remember, we need a 0.5 continually correction. So to go from a binomial distribution, we have a choice. We either go to probability of X larger than 10.5 or 9.5. Before we do that, let me just make sure everybody understands. When we go from binomial distribution to normal distribution, Normal distribution is a continuous distribution. Therefore, if you have and keep the probability or you don't keep it makes no difference. The endpoint has no effect. Remember that. That's why in many cases one may lose it. But you put the equality or not does make a difference for binomial distribution and not for normal distribution. So with that being the case, it's very simple. X is larger than or equal to 10. So what do? When we go to normal distribution, what happens? Are we going to go with 9.5 or 10.5? Which one and why?
9.5 because it has to include 10.
Beautiful. And that's it. That's all I want you to notice, because if you notice that, you don't have to memorize anything. Look at the endpoint for binomial distribution, namely 10. This does include x equals 10 because of the equality. And then it goes to 11 and then 12 and all the way to n and happen to be 200. So when we go and change it to a normal distribution, 10 shouldn't go away. So if you change this to 10.5, 10 won't be there. And you change it to 9.5. And that's really the key. You don't have to memorize anything when you want to figure out what happens as you make the transition from one to the next. All right, so now what we have is a normal distribution, and we said we need 9.5. So as we can see at the top, z equals x minus mu over sigma. So we replace the x with 9.5. In the previous step, we have already calculated mu and sigma. Therefore, we can easily calculate the z-score, negative 2.48. Now, what you should do at this point, so we went from binomial distribution to normal distribution, and this is standard normal distribution. And from standard normal distribution, I like to do the graph. So we want it to be larger than, let's say, roughly here, anything to the left of negative 2.48, almost 100%. In other words, if this was a question in the form of a multiple choice, in many cases, we should be able to answer without even looking things up, just by knowing this is almost 1. Probably the answers is only one of them that is extremely close to 1. I'm assuming. But if, let's say, there are 2 answers close to 1, then you have to look it up. If I were given this question, and if it was a multiple choice, and just for the sake of argument, one answer was 0.99, one answer was 0.9, one answer was, I don't know, 0.4, and one answer was 0.7. I wouldn't really look it up because it is definitely larger than 0.99. And why is that? Negative 2.48. Remember, from negative 3 to positive 3, it covers everything almost, 99.7%. Now, on the right side, it's going indefinitely. On the left side, it's not going as far as negative 3. Now, the next one says at most 15. So first, let's write the concept of at most 15 when it comes to binomial distribution. So this is what we are dealing with, at most. Whenever we are dealing with less than, or equal, whatever, then we just add or subtract 0.5. In other words, when we want to go from binomial distribution, the next step is standard normal distribution. We have to change the number 15 to either 15.5, we are adding, or 14.5, we are subtracting 0.5. Which one and why?
You're going to add, so you can include 15, so 15.5.
Absolutely. That's why it's extremely important. When you see this one, you should recognize it means x is 15, and then we want it to go down, so x is 14, and all the way to 0. But 15 is there. So if I put 14.5, the very first discrete or integer less than 14.5 is 14, and therefore 15 is out. That's why I'm going to add. So this way, again, I don't have to memorize, okay, in this case I add, in that case I just logically you decide. It's very logical. So with that being the case, we are going to repeat the process. What is the process? We are going to go from binomial distribution to normal distribution, and now to standard normal distribution, we calculate the z-score, and we replace the x with 15.5, resulting in z-score of negative 1.06. And so all you have to do, look it up. And to me, graphing is important. So let me actually do the graph up here. So we want the probability of z being less than negative 1.06. This is, again, not to scale by any means, negative 1.06. And we are interested in finding this area. If you look up the negative z-score, you have the answer. So again, why is the graph important? We have an idea what it is supposed to be, okay? If we are given a couple of choices that we don't need to look up, we can always handle it this way. All right, let's go to the next example.
In one of Mendel's famous hybridization experiments, he expected that among 580 offspring peas, 145 of them, or 25%, would be yellow, but he actually got 152 yellow peas. Assuming that Mendel's rate of 25% is correct, find A, P of exactly 152 yellow peas, and B, find the probability of getting 152 or more yellow peas by random chance. That is, given n is equal to 580 and p is equal to 0.25, find p at least 152 yellow peas.
We are looking at what type of a distribution. We are dealing with an experiment, and it's either yellow or not. That's really the bottom line. So the percentage of that color. So if that is the case, practically becomes a binomial distribution, because in the case of a binomial distribution, the main thing is having two categories, two outcomes, in which case we need to have two things, n and p. So if that is the case, what is n and what is p?
N is 580.
Perfect. And p?
0.25.
It's a binomial distribution. N is 580, p is 0.25. And before we move on, look at the rest of this stuff. We are using approximation. Therefore, we need to see if NP and NQ are large. So very fast, it is a binomial distribution because N and P are as follows, 580 and 0.25. This results in Q, 1 minus P, 1 minus 0.25, or 0.75. We calculate the product of NP and NQ. Both of them are large. Therefore, we can do the approximation. How large is good enough? Larger than or equal to 5 at least. So to do the math here, we're going to repeat the stuff we have done. Remember, we're going to deal with the binomial distribution, normal distribution, and so on. Therefore, let's start with the calculation, the basic calculation we will need later on, which means finding mu. That means n times p. Finding sigma. That means square root of npq. So let's calculate that. Mu equals np has been already calculated as 145. Sigma, when we multiply them and take a root, becomes 10.4283. Notice it's a good practice to carry a lot of decimals. And if you are rounding, you round it at the end. And that's extremely important. So with that being the case, the first part is asking for the probability of exactly 152 yellow peas. That means probability of x equals 152. Probability of x equals 152. When you have one value to go to normal approximation, you introduce the 0.5 continually correction factor, so you add and subtract both. So x is in between 151.5 and 152.5. The next step is SND. And to go to SND, standard normal distribution, you have to calculate the z-score. To calculate the z-score, x minus mu divided by sigma, and we have already calculated mu and sigma. We plug it into the formula, As far as the graph is concerned, always interested in the graphing the z. But just for the sake of argument, if we want to stick with this, and I will show you the z in a moment, 151.5, 152 is a small strip. So therefore, a small probability is expected. And we calculate the z-score accordingly. And for 151.5, we get about 0.62. For 152.5, we get about 0.72. And therefore, the z-score is between 0.62 and 0.72. Again, you look up the table to come up with the answer. I would have done so between 0.62. You look up the table to come up with the final answer, and it gives you the answer as you can see here. It's a tiny answer, 0.0318. So there is a 3.18% chance that exactly 152 yellow peas exist. Part B, we want to find the probability of getting 152 or more. So at least 152. That means X is larger than or equal to 152 when it comes to a binomial distribution. So here's what's going to happen. We need to add or subtract 0.5. Which one? Are we adding 0.5? In other words, we're going to change this to 152.5. Or are we subtracting? We are changing it to 151.5. Which one and why?
You're going to subtract so you can include the 152.
Perfect. Again, understand the binomial distribution means you need 152 and anything beyond that. So how do you make sure 152 is there? If you pick 152.5, the first discrete number after that is 153, and you're going to miss the first one, which is 152. Therefore, you're going to go down to 151.5. Now, z-score, I think by now everybody knows how to handle the z-score. Z is x minus mu over sigma. So all you have to do, plug in. So z is x minus mu. It was calculated in the previous page as 145 over sigma of 10.4283. And so here's your z-score. And again, I would have gone with the graph of the z-score. So larger than 0.62, something like that. This is z-score of 0.62. Looking it up from the table, we end up with 26.76%. So 1 minus 0.7324. Or you can look up by symmetry, you can look up the probability of z less than negative 0.62. This is the same as the probability of z less than negative 0.62. So if I'm reading from the table, I take the easy way out. Instead of having to subtract the number from 1, I'm going to read the negative z-score of 0.62, okay? Negative 0.62, that gives me the answer. You can see the binomial distribution, the graph, and technology. Other than TI, you can explore with other technology, and the explanation is in the text, such as stat disk, and this is what you get.